Okay, some notes on the magnetic field. Examples of field. The amount of gravity force per kilogram if we put a mass there. So that's the ratio of gravitational force per mass. That's the first field we encounter in physics. The second is, and we just recently talked about this, the electric field. That's the electric force per coulomb. So that's in newtons per coulomb. And now finally, a third field, the magnetic field. That's B is the unit for magnetic field intensity. And that's a ratio of magnetic force to a charge, but also a velocity, since in order to experience a magnetic force, you have to be moving. Put that in the right spot here. There we go. So unit-wise, what have we got? We've got force units, so that's going to be newtons. Then we've got charge units, which is coulombs, and velocity units, which is meters per second. So that's a pretty unwieldy unit for magnetic field. So we call it something. We call that a Tesla, and use the capital T, named after Nikolai Tesla. Now, electric field is produced by static non-moving charges. To get a magnetic field, the charge actually has to move. So here are some typical sources of magnetic field. The Earth, there's circulating liquid iron and nickel and things like that moving through the core of the Earth. So we think that creates the Earth's magnetic field. Current flowing through a wire creates a magnetic field. Bar magnet, well, what's moving there? Well, I suppose it's the electrons zipping around the atom and creating magnetic moments there. Coil of wire, obviously current going through the wire there. And then the largest magnetic field we've ever created is in a Tokamak, and that involves, again, a whole bunch of coils, but tremendous amounts of current flowing through the coils because this is bathed in liquid nitrogen, and the wires are superconducting, so they have no resistance, so you can run hundreds of amps through them and create a really large field. All right, so magnetic field patterns. Magnetic field is away from north and towards south. So that's a little bit like electric field, which was away from positive and towards negative. Now, compass needles will line up with the magnetic field, and we can drop little iron filings on top of a magnet to see the pattern as well. So first off, we've never actually observed magnetic monopoles. So we've never seen a single north by itself. But if we did, it would look like that. A single south by itself, we would have field lines coming in towards the south. But again, those have never been observed in nature. We think they exist because charge monopoles exist, but we've never managed to observe them. Okay, a dipole would be a single north and single south, and what that field pattern would look like would be north, south. Field lines would come out of the north. Let's try that again. Give myself a bit more room here. South, north. You can just superimpose this on the diagram. Field lines come out of the north and go into the south, out of the north into the south, away from north into south, away from north into south. So this would be the magnetic field pattern for a dipole. You just superimpose it there. Now, like poles will, of course, repel each other, and unlike poles will, of course, attract each other. Now, on the Earth, we know that a compass needle points to the Arctic, and we know, so there's the Arctic there, and we know that a compass lines up with the magnetic field, so we know the magnetic field's actually going in this direction. So this is the direction of the magnetic field here. It must be going to the North Pole. But we know that magnetic field lines point towards the South Magnetic Pole. So the North Geographic Pole up here must actually be a magnetic south. So if you were to superimpose a bar magnet on top of this, this would be south and this would be north. So this is the Arctic, it's the North Geographic Pole, but it's a magnetic south. Now we're interested in being able to calculate the field for simple geometries. The first one of interest is the straight wire. It turns out that the magnetic field for a wire is given by this expression. Mu naught, which is a magnetism constant, this is its value here, 4 pi times 10 to the minus 7, multiplied by the current in amperes, divided by 2 pi times the distance r, or d here, away from the wire. So this is how to calculate the magnetic field intensity for a wire. Now, I is, of course, the current, and that's in amperes, or amps, and R is the perpendicular distance from the wire. And that's going to be in meters. Oops, meters, there we are. And I misspelled perpendicular. There we are. Okay, now, the direction requires a bit of our attention because the direction is going to be tangent to a circle around the wire. We say the magnetic field curls around the wire. And this is the first of the famous right-hand rules in physics. What's the right-hand rule say? It says grab the wire with your right hand, thumb lined in the wire, current direction, your fingers show you the curl. So right here, with the current going to the left, you grab it so that with your right hand, your thumb points to the left, and observe the direction of your fingers curling. You see they're going up in the front of the wire and down in the back of the wire. So on top of that diagram, you can just superimpose this. So the curl is going to be going up in the front, and then it's going to be going down in the back. So that's the direction that the magnetic field is curling around that wire. If we have a current into the page, and again, you could just superimpose this on the diagram. Now we've got to stick our thumb in to the page, and that little X symbol means away from us. And if you do that with your right hand, you'll notice that your right hand fingers are curling in a clockwise direction. So the magnetic field pattern is curling around the wire in this way. And you can superimpose that on top, or here, maybe I'll just send it over here. Why not? Perfect. So this is the right-hand rule to find the field of a wire. Next, let us now take that wire and bend it into a loop. Now we see that there's current going to the left here. And again, you superimpose, I'll do it here. So current going to the left, that's right rather. So take your right hand, point your thumb in the direction of the current, and observe the curl. You should see the curl is coming down in the front, like that. And then if we follow this current all the way around the loop like this, and observe the curl, we see that in each case, the curl is sort of pointing into the page here. So the magnetic field B is into the page everywhere in this loop. And then when we get back outside, once again, it's going like this. So it's coming out at us here, and it's going away from us here, everywhere underneath the wire, and then everywhere in the center of this loop. So all those little fields are going to add up inside the loop and give you a really large field, okay? Now, on the outside, observe that this field from this little bit of current is actually coming towards you, but this field, because this wire will create field everywhere over here, this field is still going into the page. So there tends to be a cancellation of the field on the outside. We can repeat that over here. This field from this little bit of current is coming out towards us, but the field from this little bit of current everywhere on this side is going to be going away. So the field outside cancels, but the field inside adds together, so you get a nice big field at the center of that loop. So now, and you can just, again, superimpose that here. Now, let us add a whole bunch of loops together, and you get a coil. Now, if you put a core in, like a piece of iron or a nail, then it's called an electromagnet, and that enhances the magnetic field. And, of course, there's lots of applications for it. Now, it's helpful to do the following. The field is going to be strongest right here at the ends. And we see that the field lines are going in at this end and out at this end. So this reminds us quite a bit of a bar magnet, where we know the field lines come out of the north end and then go in at the south end. So this is going to be the south end of the electromagnet, and this is going to be the north end. Just by analogy with this bar magnet. Now, for the intensity of the magnetic field in a coil, it depends on, once again, the magnetism constant. It depends on the number of loops of wire and the current they're carrying. But if you stretch the coil out and don't pack the loops tightly, that makes the field smaller. Conversely, if you pack the coils in really tightly so that the coil's not very long, that makes the field much stronger. So there's inverse variation with the length of the coil. So there's the magnetic field intensity for a coil. And this, once again, is the current in amperes. This is the number of wire loops in the coil. That doesn't have any units. And this is the coil length, and that's in meters. Now, there's another right-hand rule to find the direction of the coil field. And this, once again, says grab the coil, but when you grab the coil, let your fingers go in the direction of the current. If your fingers go in the direction of the current with your right hand, you'll see these currents are going up in the back and down in the front. If you do that with your right hand, you'll see that your right hand thumb ends up pointing to the right. So these are the currents in the windings. The magnetic field is coming out at this end. That means it must be going in at this end. And here in the center, it's also going in a rightward direction. So this is the magnetic field direction for this coil. And you can just superimpose that. Here we have a coil in end view. So we imagine sort of holding onto a pop can and curling our fingers around the pop can. If you do that with your right hand in the direction of the current, you'll see that the field is actually coming up towards you. So make your right hand fingers go this way. Your thumb is going to point out at you. Out at you is a dot. So the magnetic field is out of the page here. And those are some preliminary comments on magnetic field, direction, as well as the field of a coil and field of a wire. Okay, so Ampere's law is sort of the equivalent of Gauss's law, but for currents. And what Ampere's law says is that if you've got a current, then you're going to get a magnetic field that curls around that current in a right-hand sense. Now, we'll define curl as adding up the magnetic field times a little bit of length along the path dl. Now we'll take the dot product, which essentially just makes sure that those two are parallel to each other. So that's a little bit of distance. And then we'll add that up as you go all the way around this loop. So this is a loop integral. And what Ampere's law says that integral, that loop integral, adding up b dot dl, b times the length as you walk around, that is proportional to the current that's enclosed inside this loop, the current that's actually passing through the center of the loop. So add up b dot, here it says ds, s just means a little bit of path length, is mu naught, which is the magnetism constant, 4 pi times 10 to the minus 7 times the enclosed current. Now, if we pick our path appropriately, then B will always be parallel to ds, so that the dot product just gives us BDS. And then if we pick our loop appropriately, our Amperian loop, the magnetic field will be constant. And then if we add up ds all the way along the loop, that's just B times the length of the loop. And then it depends on the shape. For instance, if it's a circle, that would be 2 pi r. But if it's a nice straight line geometry, then it would just be L. So as was the case with Gauss's law, we never actually evaluate this integral. We just make sure we pick the correct symmetric Amperian loop so that this line integral, this loop integral, always simplifies to b times the length of the loop. Let's try a couple of standard examples. So first of all, just a current carrying wire. Okay. So here we've got a wire carrying current I, and then our correct Amperian loop is just a circle surrounding the wire everywhere a distance r away from it. And so the magnetic field is going to, by symmetry, be the same. It's going to follow this loop all the way around, and it's going to be everywhere parallel to a little bit of unit length. So when we go to evaluate the curl of the magnetic field around the loop, this could be ds or dl, and then we're going to set it to mu naught times the enclosed current. So on this side, the first thing to note is that b is parallel to ds, so you can drop the dot product and drop the vectors. Then if we're the same distance from the wire, the magnetic field will have the same value everywhere on this imaginary Amperian loop. So if it's constant, you could pull it out of the integral, and then adding up ds just gives you the length of that loop. And given that it's a circle, that's 2 pi times the radius of that imaginary loop. Now, on the right-hand side, we need to think about the enclosed current. Well, the current that passes through the loop that's enclosed by the loop is all of the current. It's I. And so we return to the relationship we derived earlier for the magnetic field of a straight wire, mu naught I over 2 pi r, where mu naught is 4 pi times 10 to the minus 7. Let's try another application of Ampere's law. Okay, so now let's use Ampere's law to find the field of a coil. So first we'll draw the coil here. And then we'll say current I is coming here, which means it's going up in the front and then down in the back. And so we know, based on our coil right-hand rule, that we'll get a magnetic field in this direction. So for Ampere's law, we construct an imaginary Amperian loop. And let's have a loop here that's very long. This goes all the way up to infinity. And then it swoops down here, and then it goes through the center of the coil like this, and then again way up there to infinity, and then it rejoins this side of the wire. So I want this to be very, very, very far away so that the magnetic field is essentially 0 way out here. Now, applying Ampere's law then, the curl of the magnetic field around that loop is mu naught times the enclosed current. Okay, now the curl is going to involve adding up b times a little bit of length on the inside, adding up b times a little bit of length on the long arms of the loop. That's this side here and this side here, and then adding up b times ds on the infinitely far away horizontal portion. Now, way, way far away, the magnetic field is going to go to 0, so that'll be 0. On the long arms, well, the right-hand rule tells us the magnetic field is to the left here, but then it's going to loop around, and as it returns, it's going to cut through these long arms perpendicular to them, so that the dot product is 0. B has no component in the direction of the loop, so this is just 0. Through the center of the coil, B is nicely following the length of the loop, ds, so you could drop the dot product. It's constant and uniform, as we've shown earlier, so B gets pulled out. And then integrating ds, well, that's just going to equal the length, and let's call that length L. So this is going to be B times L. That's the curl of the magnetic field around the green loop. Now, passing through the loop, we've got current I. Each one of these currents enters and passes through that loop. Well, if there's n wires there, then that's Ni as an enclosed current. And then for the magnetic field, oops, I forgot the mu naught, because it's mu naught times the enclosed current. For the magnetic field, then, it's mu naught Ni divided by the length L, which is the familiar result that we quoted earlier. And we've now proven it using Amperes law. So Amperes law is similar to Gauss's law. It's always true, but it's only useful for symmetric charge distributions. And then you have to pick the correct imaginary Amperian loop. And the loop that you pick needs to have a B that follows the ds and that's constant everywhere on the loop. If you can do that, then Amperes law is useful to calculate the magnetic field.